So let's start our talks. Good morning. I'm chairman today, so I will probably, you have 45 minutes, yes?
Yes, I guess.
So it's like 10 to 10.
I might exceed a bit, but hopefully not. Anyway, I'll try not to.
Sure. Today's talk is of Takato Yoshimura from the University of Oxford, and the title is Ballistic Microscopic Fluctuation Theory for Integrable Systems. Please.
Thank you. So, hi everyone. Let me first thank the organizers for the kind invitation. It's been a great pleasure to take part in this wonderful workshop, although I'm not really a high-energy theorist or string theorist. So, what I'm going to talk about today is based on my recent work with Benjamin Doyon, Gabriele Prefetto, and Tomohiro Sasamoto. And the motivation of this project was, at least the initial one, was basically to devise a theory that can describe the large deviation properties of many-body systems, could be quantum or could be classical, in a systematic way. And what I mean by large deviation is simply, for instance, current fluctuations. So we wanted to characterize the properties of current fluctuations. But as it turns out, not only does this theory, so this ballistic macroscopic fluctuation theory, do the job, meaning that it can describe the large deviations of many-body systems in a systematic way, but also it can actually provide a new kind of way to compute quantities that should be also of interest to you. For instance, dynamical equation functions. So I'm going to put a bit more emphasis on that, and these are basically what I'm going to talk about today. So, to set a stage and to be a bit more precise about what I'm going to do, let me introduce a kind of quantity that I'm interested in. For instance, I'm interested in evaluating this kind of dynamical equation function that involves an arbitrary number of local observables, these guys, that are inserted at arbitrary space-time positions. And this average is done with respect to, say, local thermal equilibrium, or it could be local GGE if your system is integrable. And it's usually written in this way, where the inhomogeneity, if your system is inhomogeneous, is encoded through here, which is a Lagrange multiplier. Well, in this case, simply the inverse temperature, because H hat is the Hamiltonian density. And the length scale that over which the state is varying is controlled by this parameter small l, which is eventually sent to infinity. So that's the kind of setup. But of course, the theory, ballistic macroscopic fluctuation theory, BMFT, that's the acronym of the theory, doesn't quite allow us to really compute this kind of quantity for arbitrary space-time positions, because that's simply too good to be true. So instead, it demands us to focus on a particular situation, which is what we call the Euler scaling. So we have to take a particular scaling in order for the theory to work. So what would be the scaling? Well, simply stated, we have to take xi's and ti's to be very large compared to all the microscopic scales, but still the ratio of these guys, xi and ti, so xi over ti, should always be kept finite. So this is the kind of scaling that I'm going to work with. And basically all the kind of statements, well, not all, but most of the statements I'm going to make are valid only under this kind of circumstance. So that's something you should bear in mind. But still, I guess it's kind of interesting that if you focus on that kind of situation, you can say really a great deal about this kind of interesting quantity. All right. So before jumping into the detail of the theory, perhaps it's nice to just, at least try to do the usual thing and see what we can do about it. So what I mean by that is just to write down the usual Feynman path integral formula for this kind of dynamic equation function, let's say for simplicity evaluated with respect to some thermal equilibrium. And it should read like this. But I guess the moment you write down this kind of expression, you realize that you're stuck because you don't know what to do. I mean, how to proceed. Because, for instance, these local observables are supposed to be quite complicated in terms of the fundamental field. And also, if your theory is non-trivial, I mean, not a free theory, then the Lagrangian is probably complicated. So, I mean, in any case, you know that this isn't quite the way to go forward if you really want to compute this kind of thermal correlation function. So, the question now is, what could we do about it? Could there be a more efficient way to compute this kind of correlation function? And the answer is yes, if you really work with the scaling that I just mentioned, because on that scale, the only only relevant degrees of freedom that matter are those that are protected by the conservation laws, meaning that, for instance, energy conservation law or the momentum conservation law. Or if your system is conserving U1 charge, then of course that should also be taken into account. So, but yeah, right.
Do you assume also that beta is large?
Beta is large.
I'm asking.
No, we don't really assume that it is going to be valid for arbitrary beta, so long as it's far from.
That T is large. If T is large and then there is some periodicity in beta, then beta should be also large.
Okay, maybe that's because I'm writing this way, so perhaps this isn't quite nice. Might not be a nice way to write down the path integral formula. I mean, sorry, the correlation function. I mean, what I can tell you is that the theory that I'm going to tell you about is going to work for arbitrary temperature, so long as it's sufficiently far from the ground state. But time should always be large. That's the kind of condition you have to work with. Maybe that's not really quite clear from this expression, but that's the condition that I would demand. Okay, so, so the idea is somehow we have to exploit this kind of fact, but that's easier said than done, and the crucial point here is how to implement, that kind of idea. And it turns out that this theory we recently devised can precisely do the job. So nicely implement this kind of idea, and as a result, it provides a new way to compute the dynamical correlation function, for instance, like this, for, again, a large x and t. And a remark here is that there would be, so we need to put some kind of data to do this kind of theory, and there is only one kind of data that would be required, which is the hydrodynamics of the theory. So stating another way, if you know the hydrodynamics of the theory, you're in business. You can do this ballistic macroscopic fluctuation theory to compute dynamical correlation functions. So we have to know the hydrodynamics. That's the kind of starting point. And okay, let's talk about then hydrodynamics. Not sure how many of you are familiar with the notion of hydrodynamics. It's not that complicated.
Excuse me. I have also a question.
Yeah, sure.
But since the system is integrable, in principle,
well, so
the number.
Far I haven't really specified to integrable systems, but yeah, later on I will focus on integrable systems. But what I have been saying works for non-integrable systems too.
All you said so far is about any theory, not necessarily integrable.
Indeed. So long as the system has translation invariance, meaning that it preserves momentum cos of it.
Then my question is premature, but maybe you still will answer it later. That why at all you expect the ergodic behavior, because you have as many conservation laws as the degrees of freedom. So what does it mean then?
Oh yeah, sure. That's a good question, of course. I forgot to tell you, thanks for pointing that out. Of course, in the case of integral systems that are presumably your favorite kind of systems, you have to put all the kind of conservations that are coming from integrability. So not only the energy or momentum, these kind of low-lying conservation laws, but also you have to put all the kind of higher spin conserved charges. They have to be equally treated for the theory to work. So yeah, that's what I'm going to do actually later. So, right. So let's then start with considering a translation invariant many-body system with n conservation laws. And for the moment, I wouldn't specify the number of conservation laws because that's not really important here. But I'm implicitly assuming that, well, yeah, non-integrable systems, but actually, well, it doesn't matter. Well, it doesn't really matter, actually, if it's integrable or non-integrable. So anyway, the initial condition that I have in mind is, as I said, like this. So it's some kind of local GGE or Gibson symbol. Again, the inhomogeneity is encoded through the Lagrange multipliers. Now, in order to define the key object in hydrodynamics, I have to define a procedure called cross-grading first. So what I mean by that is as follows. So imagine you have some local observable that is inserted at some space-time point, x and t, here. And you take some extended space-time domain that includes this space-time point. Or in this case, for simplicity, I'm taking a square, but in principle, it could be any kind of domain. And this square is with size large L. And all we've got to do here is to take an integration over this domain, which we usually call field cell because it looks like a cell. And by doing that, we are basically washing out all the kind of microscopic physics that is happening inside of the cell, which we are not really interested in. So we want to kind of, preempt the kind of the possibility that there could be some kind of consequences from microscopic physics entering in the final result, which we wouldn't want to happen. So anyway, we have to do this kind of cross-graining just to wash out the microscopic physics. And there is an important inequality that we should have in mind, which is also sometimes called separation of scales. So the first bit is stating that the size of the cell, field cell, should be sufficiently larger than the microscopic scale, which is usually set by, say, in the interparticle length. But still, it should be small enough compared to the macroscopic scale that is set by this parameter. Not sorry, parameter, but it's a scale, small l. So this should, for hydrodynamics to work, this kind of inequality is always implicitly assumed. All right. Now, having defined this quantity, sorry, not quantity, but a procedure, we can define the key observables in hydrodynamics and also in the BMFT. So to define that, we have to just put these macroscopic coordinates in the argument here for the mesoscopic observables, mesoscopic cross-grained observables. And these macroscopic coordinates are there in order to enforce the Euler scaling. So I guess at the beginning I said what I mean by the Euler scaling is that xi and ti being very large, whilst their ratio is always kept finite. But this is a bit more precise way of defining the Euler scale because it tells you that the way x and t are sent to infinity is controlled by this parameter that enters in here. Okay, so this is the kind of key observable, mesoscopic observable that I'm going to be interested in. And I'm going to also treat them as fluctuating variables. And the fluctuations are going to be set by the initial condition. And this is, of course, again, a non-trivial remark, because supposedly these guys can fluctuate in whatever ways as they please. But the point here is that we are working with a particular situation, which is really a large-scale space-time. And the idea is that on that scale, all the kind of fluctuations that would contribute to these mesoscopic variables with macroscopic coordinates would be the initial fluctuation. Of course, there could be other sources of fluctuations, for instance, dynamically generated fluctuations, but they are usually subleading. And the magnitude of these guys are like square root of L, whereas these are linear in L. So they are not really going to matter so long as you take the large L limit. All right. So, okay, there are a number of interesting predictions coming from hydrodynamics. One of them is like this. So if you want to take a local average of these mesoscopic variables, again, just to reiterate, this O bar is coming from this cross-graining procedure. You know, a priori, this is quite a non-trivial kind of average, but what hydrodynamics tells you is that this can actually be written as an equilibrium average. But of course, there should be some kind of space-time dependence somewhere, otherwise it's going to be constant. And the way it's going to depend on space-time is through the Lagrange multipliers. So the only things you've got to do now is to know how these betas are going to time evolve, which I guess is a much simpler kind of task than really working at. Right. Small L is entering in this initial state. So it's a kind of scale that sets, I mean, it's a scale over which the state is really varying. So if you really take L to be infinity, then just a homogeneous case. But if you put.
So I'm confused about the following. You average on a capital L. You average on a capital L.
No. I average over this initial condition. So this is. Yep, O bar, but okay, this isn't really the averaging. I mean, this isn't quite what I mean by averaging. This is just a cross graining. It's just integrating over space and domain. Yeah, exactly. So the averaging contains the small L, yes.
No. Cross graining contains large L, but your key formula of the L contains small L. Yeah, so this formula of the line different.
Yeah.
The small L.
Yeah.
But one contains large L.
Yes, okay. O bar contains large L. So, okay, now the point is, they are in any case, they are both meant to be sent to infinity eventually. But this relation that is large L is always smaller than small L should be satisfied. So, I mean, I'm not sure what's the kind of problem that you have here. No, the point is, it's just that you prepare these cells, right? So they are like, you know, the compositions of the space into the cells. And you take cross graining. So it's, in a sense, it's like replacing each cell with this new kind of point. And this point is now taken to be macroscopically large. That's the kind of procedure what I'm doing here. So it's like cross graining plus replacing the coordinate with the macroscopic coordinate. Okay?
LS stands far away from its T. It's just on that other wall. If this one is capital L,
Yeah.
small L is sends you to that other how they are related.
So again, the small L is the, you know, length scale of the initial condition, yeah? And the cell is this big, which indeed is still big compared to the, you know, interparticle length, so it contains a sufficient number of particles. But the point is, if you look at the scale that is comparable to the small L, things are still varying smoothly. Okay? Anyway, hopefully I can make things a bit more concrete later, but are you still confused? Okay. Sorry. Right. So where was I? Yeah. So as I said, I can write down this kind of local average in terms of the Lagrange multipliers that are dependent on x and t. But the point is, you can also write it in terms of, I mean, as a functional of q's. So charge density averages are defined in this way. And this is because in equilibrium, there's a bijection between the set of betas and the set of q's. So by using that, you can also write down the local average like this. So this is what we usually call localization of averages. Right. Now, as I said, the problem now boils down to get to know how Qs or betas are going to time evolve. And this is precisely what is prescribed by the hydrodynamic equation. So, for instance, hydrodynamic equations can be written this way, where the matrix A is defined in this simple way. It's a derivative of J with respect to Q. And the C matrix is the usual susceptibility matrix. Now, there is another equivalent way of writing down the hydro equation, which is in terms of the Lagrange multipliers. And as it turns out, this is going to be useful for my purpose, so I'm going to use this extensively. Now, we know how to characterize the space-time profiles of local observables. I mean, so long as, again, we work with a large-scale space-time. But the real question now is how then the fluctuations propagate in space-time? And or to be more precise, according to which measure would O of x and t fluctuate? So that's the question to answer. But to start with, we should first understand how to characterize the initial fluctuations. So the fluctuations coming from the initial condition. So again, the kind of quantities that I'm interested in are the mesoscopic variables defined in this way. And thankfully, we know that how to characterize the initial fluctuations because people have worked on it before. So it's simply that they're going to fluctuate according to this measure, dp ini, which is given in this way. So d mu is simply a flat measure. It's a measure that you usually use in your functional integrations. But I guess the non-trivial bit is in here. So this curly f, which is given in this way. And this guy is called the large deviation function. And here, for instance, S is the entropy density. And all the quantities that are coming with the subscript ini are supposed to be evaluated with respect to the initial condition. So again, just to reiterate, I guess it is quite non-trivial that these guys should fluctuate according to this in this large deviation fashion. But well, this is all because we are working with this particular situation, which is large scale. So if you depart from that kind of situation, this isn't quite true. But this is good news because we can exploit the fact that this is taking this form, which is exponential of L times something. And it's going to be really to help us carry out the computation. So I'm going to exploit that. Just to check this is consistent, because this is, a fluctuation that is around the mean value, which is captured by hydrodynamics. So if you take the saddle point of the path integral like this, it ought to give you back the result of hydrodynamics. And indeed, it does. One can easily see that it does give you back the hydrodynamics. So this is consistent. So the question is, how are we going to generalize this initial fluctuation measure to the measure for the fluctuations of full-fledged space-time independent charge averages? Again, this is a mesoscopic coarse-grained variable with this macroscopic coordinate. So actually, we don't quite have an answer. I mean, in the sense that we don't have a derivation of the statement I'm about to make, but we have a physically sensible reasoning. So to know the measure that I mentioned, we have to assume something. And the principle that we are going to assume that it holds is what we call local relaxation of fluctuations. So what I mean by that is as follows. So fluctuating variables, these guys, the variables that I have been talking about, actually do not fluctuate independently. Well, supposedly they are, but they would be, but the claim or assumption is that they actually do not fluctuate independently, but rather are fixed functionals of fluctuating charge densities. So in terms of the equation, our assumption is this one. So question is, how are we going to determine this functional form, which is yet unknown? We can luckily do it quite easily by invoking the fact that at t equals 0, we can invoke this kind of path integral formula because we know that the initial fluctuation measure should be given in this way, as I stated in the previous slide. So we use this fact, and by taking the saddle point, we can actually see that this functional form is the same as what we used for the hydrodynamic in hydrodynamics, meaning that what we used for this kind of expression, which is a local relaxation of averages. And this is, I guess, quite non-trivial in twofold sense, because firstly, again, it doesn't have to be this way. They can, in principle, fluctuate in their own ways. But our claim is that, well, on this scale, again, everything pertaining to the Euler scale physics should be governed by the conservation laws. So in that respect, it is not too outrageous to assume this kind of form. So that's the kind of reasoning that we have. But on top of that, somewhat surprisingly, we can also see that this functional form is completely fixed by hydrodynamics. So the same kind of function form that you used in evaluating the mean values. So there's a nice parallelism between the local relaxation of averages and the local relaxation of fluctuations, which I'm going to really make full use of. Okay, so now we are in the position to write down the measure that I have been mentioning, which should read like this. So the first two bits are the same as the initial fluctuation. The third one is the new one. But it's quite trivial because it's just there in order to enforce the continuity equation. But the non-trivial bit here is that the current there is supposedly, again, could be independently fluctuating. But the assumption we just made tells you that, well, that's not quite the case, but the way the current fluctuates is dictated by the way Q is going to fluctuate. So we have to put the local relaxation of fluctuation, so the principle, in here, and we have this measure. So now we're in business. For instance, we can compute the BMFT average, so average with respect to this measure in this very simple way, where in the second line, I just exponentiated this delta function. It's like a Laplace transformation, like this. And of course, the main claim of the BMFT is that this BMFT average should be identified as the local average. So what we have to do now is to evaluate this kind of path integral. But the real point of the BMFT is that you do not actually have to evaluate this kind of path integral formula. This is because eventually, if you take this limit, small l to the infinity, everything is going to be dominated by the saddle point. Well, I said saddle points, but actually, I should remember this as because there will always be one saddle point in here. So how are we going to see that? Let's say if you want to evaluate this kind of, average of this kind of observable, you might be tempted to put that in this formula. But I guess you wouldn't then know how to proceed because it doesn't really tell you anything. And as it turns out, that's not quite the right thing to do. What you have to do instead is to put this guy, exponential of L times O, and evaluate this path integral formula. The good point of this trick is that everything is now of this form, exponential of L times something. So if you take large small L limit, of course, it's going to be dominated by the saddle point. So you can just pick the contribution from that. And that's going to spit out some kind of number like this, where this curly O is defined in this way. So just to remind you that this curly O of Q dot 0 is the large deviation function that I defined in here. And this Q star is the minimizer of the BMFT action. So in order to know the equation that is satisfied by the Q star, you have to take a variation of this action with respect to Q and H. And if you do the latter, you immediately see that Q star has to be always the solution of the Euler equation. So this is always satisfied. So what we can infer from this is that the effect of inserting the operator here, which can be also thought of as modifying the measure, is encoded solely through the boundary condition or the initial condition of this Euler equation. Or actually, it's going to be a coupled Euler equations, but anyway. So we are going to see it. To make things concrete, I'm going to focus on these two quantities. So the first one is, as I advertised, the Euler-scale dynamical equation function. Right. But the second quantity might not be so intuitively clear to you. Well, it's actually a very physically important quantity called scaled cumulant generating function. So it's basically a quantity that tells you how the currents are going to fluctuate. So it is also experimentally relevant, and anyway, so just to check the validity of the theory, I'm going to evaluate these two quantities. And to do that, you have to choose O, so the observable, this one, in these two ways. Okay, where lambdas are simply some parameters. Okay, and you immediately realize that if you follow the logic of the BMFT, these two objects should be given in these fashions. So I'm going to see how we can really compute it. Okay, now let's start with the current fluctuations. Okay, so the scaled cumulant generating function, which is simpler. So in order to know the equation satisfied by the Q star, we have to, as I said, take the variation of the BMFT action S, which reads like this. So if you solve this equation, then you know the full profile of the Q star. And once you know it, you can plug that into this formula. I didn't write down the derivation. It's just a consequence of the simple manipulations. So the scaled cumulant generating function defined here is written in this way. So if you know the full profile of the Q star, you can plug that in here and compute it very easily. So this is a much simpler way to compute this kind of object. But what we are really after here is the dynamic equation function, which is, okay, for simplicity, let's focus on the two-point function. And this is given by in this way. And again, by doing some simple manipulations, you realize that it's also written in this way. So we have to evaluate this. And Q star is going to satisfy this BMFT equation, which is slightly different from the current fluctuation case, because obviously we are talking about different kind of object. But a surprising point here is that by doing some formal manipulations, we can see that the BMFT actually predicts something quite non-trivial and a new kind of physical phenomenon, which is as follows. So imagine you try to evaluate this kind of dynamic equation function, and note that the time coordinates are the same for two observables. So they're evaluated on the same time slice. And this guy is going to behave in this way, which is highly non-trivial, because the conventional wisdom of hydrodynamics tells you that we would only have this first term, which ensures that if you start out with some local equilibrium, then this will, the structure of it will remain intact. So at any time slice, you can effectively assume that the local equilibrium is realized on each time slice. That's the kind of message you can get by seeing that this is the only kind of quantity that is appearing here. But the BMFT predicts otherwise. There will always be an additional contribution like this, which is going to decay in a so much slower way. So in terms of microscopic coordinate, this is going to decay like 1 over x, as opposed to the exponential decay coming from this one. And this is quite interesting because, even if you start out with some initial condition that has no long-range correlations whatsoever, this kind of long-range correlations, dynamically generated long-range correlations, could build up just through some hydrodynamic interactions or the correlations amongst normal modes. Well, I mean, normal modes are basically hydrodynamic modes, provided that the system is on some inhomogeneous background. So this is really coming from the inhomogeneity of the system. And actually, there are 2 other conditions that should also be satisfied for this to be happening, I mean, long-range correlation. So the first one is multiple conservation laws. It has to be having at least more than one conservation law. And the one is the interaction. So it cannot be a free theory. And the third one is the inhomogeneity. So the idea here is that, let's say your state is homogeneous. And basically, all the kind of correlations that would give rise to, and that would contribute to the dynamical correlation functions are coming from the correlations amongst the normal modes. So normal modes are basically the carriers of the slow modes. And at some time, they're going to be emit. So a pair of them would be emit. And they're going to propagate. And the point is, if the state is homogeneous, it doesn't matter where they are created. Because they, everywhere in the states, they look the same. But if your the state is inhomogeneous, then somehow these 2 propagating normal modes retain the memory of where they are created, where they are emit. So this is coming really a kind of physics that is coming from the inhomogeneity. And this, to our knowledge at least, hadn't been really known before on this scale. Actually, people knew that this kind of thing could happen on a different scale, say diffusive scale, but on the Euler scale that we are interested in, this is, I guess, quite new. So to see if this is really true or somehow a kind of, false observation that is made by some formal manipulations, I'm going to apply all this machinery to the BMFT, the integrable systems. Yeah. Okay, so how much time do I have? 7, okay, I have to be then a bit quick. Okay, so to apply this BMFT to integrable systems, as I mentioned at the beginning, the only kind of input needed is hydrodynamics. And if you want to treat integrable systems, then you have to know the hydrodynamic theory for integrable systems, which is, of course, generalized hydrodynamics. Well, maybe some of you, or maybe many of you, don't really know what the generalized hydrodynamics is. So I'm going to give you a brief account on that. So this is a kind of theory that we devised a while ago. And a key intuition behind GHD, generalized hydrodynamics, is that on the large scale, on the hydrodynamic scale, all the integrable systems are going to behave in the same way. And to be more precise, they're going to behave as if they were hard rods. So that's the kind of intuition you can get from working out hydrodynamics for integrable systems. And that is precisely why GHD is so universally applicable to many integrable systems. And hard rods are simply, I guess it's one of the simplest kind of integrable systems. It's just a bunch of rods on the line, and they scatter or collide elastically upon a collision. And interestingly, if you really look at integrable systems on a large scale, they behave pretty much like hadrons. Right. Now, the hydrodynamic equation of the GHD, so GHD equation reads like this. So the kind of beauty of GHD is that now we can write down the equation at the level of quasi-momentum. So for instance, rho theta is the particle, density of particle, whereas effective velocity, which is again labeled by the quasi-momentum theta, is some functional of rho theta, given in this way. And this var phi, this guy, here is, of course, coming from the S matrix. So it's like a derivative of the logarithm of the S matrix. So we have to plug that in here and solve this equation self-consistently. Right. Or equivalently, one can also write down the GHD equation in terms of the betas, as I will do later, by defining the beta theta in this way. Okay. So for practical purpose, I'm also going to introduce the mode that we call the normal mode, which satisfies this kind of equation. And this epsilon defined in this way. So once you know the beta, you can get epsilon by this transformation, where R, the matrix R, is given in this way. So this is a matrix labeled by the quasi-momentum, and as it turns out, it also diagonalizes the matrix A, so Jacobian matrix, and its eigenvalues are the effective velocities. And we call this normal mode because now the velocity is coming in front of the x derivative, and this is going to be important. I mean, at least for technical purpose. And a physically important remark here is that there would be no shock in GHD, meaning that there would be no sharp structure that's going to emerge as a consequence of dynamics would exist. So this is good to know because this basically implies that there will always be a unique solution of the GHD equation. And that's reassuring, and we don't have to worry about the potential existence of other saddle points. So at least so long as, as far as the integrable systems are concerned, you are in the safe position. Now, again, let's start with the current fluctuation. So this is the same thing as before. The only difference is that the indices are now quasi-momentum. And I'm treating them like usual integer indices, but for instance, this guy should be thought of as a direct delta. And here hi of theta, which I redefined in this way, is simply the one particle eigenvalue of the charge Qi. To go forward, we also have to define the normal modes associated to this field, H, auxiliary field, which appeared as a consequence of the exponentiation of the delta function. And the way we do it is based on how we define the normal mode for the betas. So this is the way we define the normal mode for the H. Right. This is just a way of doing manipulations. And we have now this, so two equations of these BMFT equations can be now written in this way in terms of the normal mode. And the reason why we did this is because we can then use the method of characteristics to compute this kind of profile. And what I mean by the method of characteristics is that if you want to know this kind of field profile, the only thing you've got to know is the profile of this guy at t equals large T. So this is a final time. And once you know that, you can get this field profile, provided that you can evaluate this r theta of x and t. But this is so much simpler task because this is going to satisfy some simple integral equation. So if you solve the integral equation, you can obtain this r theta of x and t and get this full profile. I didn't write down the integral equation satisfied by the r theta, but it's not that complicated. Anyway, so at the end of the day, you reach this kind of, I mean, you can recast the whole MFT equation into this form, which is the GHD equation with some very non-trivial boundary condition. So you have to work out this equation, which is not always feasible, but in principle you can do it. For instance, in the homogeneous case, let's say thermal equilibrium, you can evaluate the Taylor expansion coefficients of the cumulant generating function, which we call cumulants simply, and they read like this. For example, the second and third one read like this. I didn't really write down some definitions of the quantities because they're not so important. What I want to say here is that simply you can work out. Things could be a bit messy, but in principle you can work out. And these are also in agreement with the previous predictions from different theory, and also agrees with the simulations. And the nice point of the BMFT is that one can also easily extend these things to inhomogeneous cases when the initial condition is, not really homogeneous anymore. And for instance, if you pick this kind of initial condition, which is a particular initial condition, a step profile initial condition, if you like, then you can get this kind of second cumulant in this way, which is somewhat surprising, again, physically, but I guess I don't really have time for that. So I'm going to skip quickly. This is just to show you that it really agrees well with the numerics. And this is just a cartoon picture of the hadrod system with the Hamiltonian being like this. All right. But what we are really caring about here is the dynamical coefficient function. So we can proceed as in the current fluctuation. And we eventually obtain this kind of GHD equation with the boundary new non-trivial initial condition. And after some cumbersome manipulations, you also can obtain the exact formula for the long-range correlations, which are really messy. We have to solve all these things in a self-consistent way. I didn't, again, mean to write this to be informative. This is just, I wanted to say that one can really compute this kind of thing once you're really determined enough. So one can do it. And if you really do it, you get, yes? Yeah, sure. So I'm going to finish in the next slide. Yeah. So these are just the numerical checks for these results, and they really agree very well. Okay, so sorry for the bit of delay. I guess just talk about the outlook. So BMFT is really unified theory, so naturally it really opens up a variety of new directions. It would be nice to verify it microscopically because it's a phenomenological theory, and also it would be nice to apply that to a different transport type, like superdiffusion, a superdiffusive transport, and also it would be nice to say, for instance, compute something of quantum nature, let's say entanglement entropy, like time evolution of the entanglement entropy, or incorporate the quantum fluctuations. They are, I guess, all equally very exciting directions. So anyway, so with that, thank you very much for your attention.
Thank you. So please, questions.
I would like to ask the physical meaning of this capital R operator, because we face with the kind of similar quantity in calculating finite size form factors.
So I guess you mean this one, yeah? It's just a dressing operator. So if you, for example, I guess defined somewhere up here. So if you, for instance, say for some function of theta or phi, you can just apply this and get the dressing equation.
But dressing in which sense? What dressing interaction or
Yeah, dressing
dressing?
interaction. So I guess it's a bit different from the kind of dressing that is usually used in the integrable system community, but this is just a way to incorporate interaction. So what you get as a result is that this guy is going to satisfy some integral equation that looks pretty much like this. So just a way to incorporate interactions.
So in finite volume calculations, usually this is how you take into account the finite size effects order by order of the particles. So is it a finite temperature effect here, or what?
Yeah, so indeed, not the finite volume effect, but the finite temperature effect. So it's a way to incorporate the kind of state.
Thank you.
More questions? Actually, I had a question which is maybe a continuation of Zoli's question. Can you play here these games of analytic continuation to beta, to imaginary beta, like we do in homogeneous systems to compute this Alexei Zamolodchikov trick? You compute the thermal equilibrium, then you do analytic continuation to compactified space. Or this inhomogeneity destroys completely this analytic structure.
I'm not sure about this analytic continuation thing. So,
say you
so
have
space is purely
inhomogeneous, I don't know how to formulate, inhomogeneous distribution of temperature versus inhomogeneous spatial circle distribution of.
So, okay, you mean the periodic condition for the state, not for the system, but. But what would it mean in this case? It just. I can't quite imagine what kind of state it would be. I mean, maybe it's possible, but and if the circle of the beta is really large, then maybe it makes sense because it's going to be weakly changing. But still, yeah, not sure what exactly it means.
Okay.
So,
Thank you. There is a question there, Benjamin.
Yeah, thanks for the nice talk. It's just a naive question. I was wondering, is there anything interesting? I mean, could it be interesting to look also at theory with non-diagonal scattering? Or
yeah, I guess you can easily do that for non-diagonal things, systems, because GHD has been applied to non-diagonal theories like a Fermi-Hubbard model. So we know how one can do GHD for non-diagonal systems. So, and as I said, the BMFT requires only the hydrodynamic input. So if you know the hydrodynamics of the theory, you can do it. But I'm not sure what would be, something extra interesting. I mean, if you deal with the non-diagonal systems, I mean, there would be always long-range correlations, like I explained here. But that's not really, to do with non-diagonal scattering or anything. It just it would be there always. So you can do it.
So it's not giving rise to new behavior, or it's more or less the same, you're saying?
I guess more or less the same, but maybe there could be interesting physics that I'm not really aware of. But yeah.
Okay, thank you.
If there are no more questions, let's thank the speaker.